Today I'm going to lecture a little bit on Chapter 8 on general knowledge. And basically, kind of from a cognitive psychology perspective, we're going to be talking a little bit about how kind of general knowledge of the world is structured within our cognitive faculties and within our brain, if you will. Um, how is it, or what do we know about we know what semantic memory is? It's memory for facts. But then how are facts kept in memory? Like, how are facts structured in memory? What are some of the principles we know about that? Now I'm going to actually go through several different theories of how we retain different kinds of concepts and how those stay cognitively within our own minds. They're not necessarily mutually exclusive, meaning that they don't have to necessarily cancel each other out. It's probably the case that different theories are going to be active at different times and based on different things. The context will change. So let me go ahead and start on this and kind of give a little bit of background information, and then kind of move on through. So first off is this idea of the situated cognition approach. And if we remember when we were talking about embodied cognition, it's a very similar sort of thing. And that is our knowledge depends on our current contexts, meaning that the places we are in, the objects that we are around, the setting that we are in has a big effect on what types of things we have in our memory and what types of concepts easily come to mind. So when we think about semantic memory, it allows us to do several things. It allows us to organize objects according to different concepts. It allows us to make inferences going beyond what the information is given. And then allows us to decide which kinds of objects are similar. So we can organize objects by what kind of concepts there are. We can make inferences. And an inference is basically knowledge that goes beyond what we see in like a sentence. So if we have a specific sentence, for each word in that sentence, we can make inferences about what other things might be true, even if it's not in the sentence itself. Meaning if there's a sentence about a bicycle, we know all different kinds of information about bicycles in general, and we can make inferences about things. Or based on the context, based on what's happening in the sentence, we'll make inferences about how old someone is, where they're from, those kinds of things, and that's what an inference is. And then two, one of the interesting things that we'll be talking about in general is the way in which we categorize or group things together and how we make distinctions in terms of categories. So the first approach that we'll start with is the prototype approach, and this was developed by Eleanor Roche. Started in early to mid 1970s. And what she argues is that we organize each category on the basis of a prototype. And a prototype is an item that is most typical and representative of that category. So the idea is that when we're talking about things like, say, a bird, we have a prototypical bird in mind, and that prototype is the basis for how we categorize different sorts of things. So the prototype approach is basically we decide whether an item belongs into a category based on comparing it to that prototype. So categorization is dependent upon similarities and differences that we observe based on comparison to a prototype. That is the prototype approach. Now what's important is a prototype is basically an idealization. So it's more of an ideal prototype rather than something that exists in reality per se. Obviously the prototype is going to be really connected to things that we know, but the prototype approach is slightly different from something we'll look at a little bit later, which is the exemplar approach. And in the exemplar approach, contrasting with the prototype approach, for the exemplar approach, we have a specific thing in mind in the real world. And so an exemplar is an example of something, and it's the best example we have of that category. The prototype approach is more, in a sense, abstract and, if you will, cognitive, meaning that we have kind of an idealized representation of a prototype that is going to certainly be very similar to things that we have in the world, but it's going to be more of an idealized version of those things. Roach argues that members of a category differ in terms of their prototypicality, how close they are to that prototype, and that there's a graded structure within categories. So when you have a specific category, there's going to be a certain amount of gradation, or if you will, changes in how much each thing in that category is just like the prototype. So obviously, if we think about the example of a bird, in a lot of research that's been done, a robin is something that's most likely or closest to a prototype. We have kind of a prototypical bird in mind. And so a prototypical bird of mine typically has it has wings, has feathers, and it flies. Now, when you think about things that are within that category, then things like an ostrich or a penguin have less similarity to that prototype. So we still kind of keep them in that bird kind of category, but they're not nearly as close to the prototype as other things. So if you think of a prototype of a bird, then like a lot of different kinds of birds, eagles, hawks, bluebirds, cardinals, like there's a lot of different examples of things that are pretty close to that structure. But then as we move out, we can, as things change in terms of size, and in terms of other sorts of parts of that prototype, or things that are related to that prototype, we'll see that there's a gradation in that structure. So in terms of looking at some of the research and some of the characteristics of different types of prototypes, when you supply prototypes as an example of a particular category, items rated most prototypical for a particular category were the same items that other people had supplied most often in their category norms. So what that tells us is it seems to be the case that people tend to have similarities in terms of what they think is a prototype, meaning that they seem to share certain ideas about what a prototype actually is and what characteristics should actually be associated with that particular prototype. These tend to result in what's known as the atypicality effect. So when we're judging whether an item belongs to a particular category, typical items are judged much faster than atypical items. So if you go back to that example of the bird, typical items like a wing and a feather seem to be judged most likely, or they're judged much faster than other types of they're judged more faster than atypical items, or items that wouldn't necessarily be associated with that particular category. Prototypes are often tend to be judged more quickly than non-prototypes after semantic primings. So when you prime someone semantically, meaning when you prime someone with the meaning for something, people tend to respond faster to an item if it was preceded by an item with a similar meaning. So if you prime someone with, say, the word like flying, it's much easier to get into the prototype of a bird than some other type of prototype or other type of a concept when we're looking at something. So semantic priming, meanings seem to beget different kinds of meanings, or meanings cause people to have similar sorts of meanings and to retain that specific knowledge. Priming also facilitates responses to prototypes more often than it facilitates responses to non-prototypes. So the prototypes tend to come to mind faster when someone is primed, rather than things that are non-prototypical for a particular sort of thing. And then also, priming tends to inhibit judgments associated with non-prototypes. So it tends to take away from our ability to think about things that aren't a part of that particular prototypes. And what that tells us, or what a lot of this research really shows, is that prototypes are judged much more quickly than non-prototypes, because they come to mind more and they're more a general part of that particular category. Prototypes also tend to share certain attributes in what's called a family resemblance of a category. So, what family resemblance is, or as they've looked at how prototypes really work, family resemblances, there tends to be several different attributes that are shared within a category, but there's no one single attribute that's shared by all examples of a concept. So any concept you have, there's going to be a certain amount of variability, and they're all going to be encased in that category or that concept based on family resemblance, meaning there's a certain amount of similarity that's there, but it's not that they are either all exactly the same, nor do they all have the same attribute. Instead, it's a family resemblance. There is a way of finding certain connections based on how similar they are to the prototype that defines what that concept is, but there's no one thing that determines whether or not something will be thought of or placed into a particular concept in the category. When we think about something like a family resemblance, it's not the thing that any one thing is shared by all example, but at least one thing connects to another thing or another part in that category. So even if there's a lot of different kinds of birds out there, and maybe they have different kinds of wings, there's still going to be a connection between individual birds within that concept of what a bird is. So there's no one thing that defines every bird that we put into that particular concept, but there's overlap between different items that appear within a particular concept. In one study that was done by Rorsch and Mervis back in 1975, they looked at prototypicality judgments among members of several different categories. And then they had them list all the attributes possessed by each item. And what they found is that the most prototypical item shared the largest number of attributes with the other items in the category. So the thing that was most prototypical for that particular concept tend to share the most attributes with other items that were a part of that particular category. So there was a certain amount of similarity in terms of the prototype, or in some ways, like the prototype goes the farthest in having properties that help to unite a particular category or a particular concept. So we've talked about this a little bit, but I wanted to kind of add in a little bit more in terms of prototypes. There's several different levels that we use when we're trying to categorize something. We have the subordinate level. We have the basic level, and then we have the superordinate level, basic level, and then subordinate levels. So the superordinate levels are the higher level, more general types of categories. So those are things like tools and furniture. Basic level categories are the things that are more specific, and specificity is really in comparison to either superordinates or subordinacy. And so basic level categories are things that are more specific in terms of superordinates, meaning things like a screwdriver or a chair. So a screwdriver is a type of tool, but we kind of have more of a visual image in mind when we think about a screwdriver. And a chair is a type of furniture, so it's a part of that superordinate category. But here again, we have more of, can often have more of a visual image in mind. And it's something a little bit more specific when we think of something like a chair. Then underneath those basic level categories are the subordinate level categories. And these are underneath those kind of basic level categories. And basically they become more specific than like things like a screwdriver or a chair. So like when you think about a Phillips head screwdriver, or maybe even like a particular brand of screwdriver, that is more of a subordinate category. It's a little bit more descriptive. And when we think about a chair, we can move into a desk chair. We can think about a lot of different specific types of chairs or even specific brands of chairs. And so that gets us into the subordinate level. And for the most part, human cognition is best at working with basic level categories. That's the thing that's kind of easiest for us to grasp, most likely because we have a basic visual representation in mind of those things. So when we look at the prototype approach and we think about it in terms of levels of a categorization, the basic level names are often used to identify different types of objects. So in one study, they found that when you ask people to look at pictures and identify different objects, people tend to prefer to use basic level names. And people tend to produce basic level names faster than subordinate names. They tend to produce basic level names faster than superordinate names or subordinate names. So basically, when you see a picture of something that looks like a hammer, it's easiest to call that a hammer and not a tool, or like a specific brand of hammer or a specific type of hammer. So the basic level categories we tend to are quicker, we're faster with them, and they tend to be easier for us to process. So when we're presented with superordinate or subordinate names, people frequently remember the basic level version when later tested for recall. So even when you present either the superordinate or subordinate categories, we tend to still even remember those things in terms of that basic level version. Because the basic level version is it's a little bit more simplified, so it's easier to hold in memory and in cognition, but it still has enough specificity or difference between other things that we see to make it easy to distinguish some of those types of things. Also, when you look at basic level names, they're much more likely to produce the semantic priming effect. So when you prime with a basic level names, it's actually very helpful in terms of bringing things to mind. But when you prime with superordinate names, it's not very helpful in terms of retention or in terms of recall. So one other part of this kind of levels of categorization approach is that it seems to be the case that different kinds of categorization actually activate different regions of the brain. So it's probably the case that when we're using a different level of a categorization, it's probably the case that we're thinking about it in a slightly different way, and that corresponds to different kinds of brain activation. So superordinate terms are much more likely than basic level terms to activate parts of the prefrontal cortex. Prefrontal cortex tends to be much more abstract, and so those abstract categories are probably relying on the prefrontal cortex to kind of help us understand their meaning, whereas subordinate terms are more likely than basic level terms to activate parts of the parietal region. Okay, so some conclusions about the prototype approach. One of the primary strengths of the prototype approach in general is that it allows us to account for our ability to form concepts for groups that are loosely structured. So even it's the case, as we talked about before, that for a prototype model of um, categorization, there's no one thing that defines all of them, but there's enough family resemblance to kind of keep things in a group. And as we know, once you start to try to categorize things, things are going to vary in terms of their ability to be in a particular group. Now, we think about some of the problems that we can see that we run into with this type of approach. Concepts can be unstable, and they can be verifiable. So you can think about different kind of cultural changes that can happen over time, or even differences in language that can change how well a prototype concept can be maintained. Um, and then we often do not store specific information about individual examples of a category. And then the second problem that we find is that it's often the case that we actually do store specific information about individual examples of a category, not just the prototypes. So it does seem to be the case that even though we may have a prototype to lead us in certain aspects of the categorization process, we still hold on to specific information about the individuals that are contained within that category. So in that sense, what is the prototype doing? Meaning, if I have all this general information about each thing that's a part of that specific category, what is it that the prototype is actually doing? Is it really necessary? So this is some of the critiques or problems that have been found with this particular approach. Second example of general knowledge structures that we're going to look at is known as the exemplar approach. The exemplar approach, and the exemplar approach is different from the prototype approach in that it assumes that we first learn some specific examples of a concept, and those specific examples function as an exemplar. And then we classify each new stimulus or each new thing that we see by deciding on how closely it resembles those specific examples. So the idea is that we find one thing, and so the example here is if you have several case studies in a course on different psychological disorders, the way that you begin to categorize or formulate that information is you find, for example, one example of depression that is your exemplar example. And then you base every other case you have and decide whether or not something should be categorized as depression based on how close it is to that particular exemplar. So once again, prototypes are more based on idealizations. It's more of an abstract concept or abstract prototype that we use to categorize different kinds of concepts. Whereas an exemplar approach means that we have one exemplar, which is something that exists in the real world, something we've seen or described or something like that, and we base whether or not something is a part of that category or that concept based on how closely a new stimuli or new things that we visit match the exemplar. In one study they did, they looked at 7 basic level categories. And you're supposed to provide the first example that actually comes to mind for each of the 7 basic level categories. And then what they did is they had different students actually rate the categories and examples in terms of their typicality. Then the researchers tried to see if they could find an equation to predict the typicality of the categories based on the exemplars. And so to do this, they need to take into account the frequency and the typicality ratings of the exemplars. What they found is that exemplar frequency and exemplar typicality accurately predicted which of the 7 categories were most typical for the superordinate categories. In this case, it was animal. So the idea is that exemplars seem to do a really good job of predicting which of the 7 categories were most typical for a particular superordinate for a particular superordinate category. Then when asked a question about a category, people don't just consider prototypes. They also include information about less typical examples of the category. We saw that this was kind of a critique that we saw earlier, that there is a way that we have an exam that even though we have prototypes for certain kinds of categories, we still also have a certain amount of information about less typical examples of the particular category. And so because of that, it seems to suggest that other things might be going on besides just the prototype. So when you compare these two approaches to each other, both seem to compare a new item against a stored representation of the category. So both of these examples either compare something to a prototype or a exemplar. So for the prototype approach, it's the stored representation is a typical member of that category. In the exemplar approach, the stored representation is a collection of numerous specific members of a particular category. So here again, the prototype is more idealized, whereas the exemplar is more of the collection of very similar specific members of that category that most exemplify what it is that you're actually looking at. So one of the strengths of the exemplar approach is that you don't need to perform any kind of abstraction process. I mean, you don't really have to have a higher level concept or a higher level abstraction. You simply rely on what kinds of things you see in the real world. So this argues that the prototype approach would force you to discard useful, specific data about individual cases, where the exemplar approach probably wouldn't necessitate that kind of a discarding feature. Certain problems that you have is the exemplar approach may be more suitable for categories with relatively few members. If you had an exemplar for every little thing that you had, there may not just be enough kind of cognitive room, if you will, or enough memory to actually remember all of those different exemplars for different sorts of things. So the prototype approach may be more suitable for categories where you have many members involved. Then, of course, another potential problem is that there just seems to be individual differences, or well, at times there's a certain amount of individual difference in terms of different types of representations. So there's not always kind of exact matches for what persons use as either their prototype or the exemplar. I mean, there's a certain amount of variation in terms of which of those actually get used. So a few conclusions. Semantic memory is quite flexible. We have a lot of room and a lot of ability for semantic memories to be stretched and changed over time. So what may be the case, well, what is probably the case is that both approaches actually coexist. And based on the type of information that you're looking at, or the type of information you're either trying to recall or to place into memory, you may use different kinds of approaches based on what it is that you're looking at. Could be that these two things exist in different hemispheres of the brain. So, for example, the left hemisphere may be more made for dealing with prototypes, whereas the right hemisphere is more made for dealing with exemplars. So it's probably the case that people use a combination of prototype strategies and exemplar strategies when they're forming their categories in everyday life. And over time, it might be possible to figure out what types of information is best for a prototype, or what types of information relies more on a prototype, or what types of information relies more on exemplars. And it's probably the case that we use whatever mode is most expedient for us at the time. Okay, so moving on from prototype and exemplar theories about concept formation, we're going to move on and talk a little bit about network models. network models. And so network models provide a network style to the organization of concepts in memory. And this idea is that there's a network of interconnections within which conceptual models are actually located. So the meaning of a concept depends on the other concepts to which it is connected. So the idea is that when you network models of semantic memory are the idea that we have different nodes, and those nodes have certain words for, well, probably better to say those nodes have different concepts, and then the nodes are connected to other concepts that allow us to make meaning out of what it is that we're looking. And this is the idea of spreading activation. And that's the idea that a meaning is found based on its spread across a network of different meanings, or a network of different concepts. And that the meaning is found in some ways kind of more holistically within the entire network. So you have specific nodes, and it's the interconnection of several nodes together that allow us to make meaning out of a particular concept, or even within a particular sentence. Now, one network model that's more recent, if you will, is Anderson's ACTR approach. And ACTR stands for Adaptive Control of Thought, Irrational. And adaptive control of thought attempts to account for a wide variety of different cognitive tasks, including more a declarative knowledge. And so a declarative knowledge is more of the things that is our factual knowledge that we have, but that's also contained within a propositional network. And a propositional network is the smallest unit of knowledge that can be judged either true or false. It's more of an abstract representation. So declarative knowledge is in some ways more, well, declarative knowledge would contain some amount of propositions, but declarative knowledge is also about kind of basic meanings that we have. But if you think about at least part of those meanings, it's also about certain kinds of propositions. And so the propositions are determined to be true or false based on their place within the network. So according to Anderson's ACTR approach, each concept is a proposition that can be represented within its own network. Practice over time increases the strength of the links between the nodes. And this is the idea of as you're working on learning something new, as you practice something, as you work to try to recall those things, as you work to understand its meaning, the more practice that you do with that concept and understanding what the concept means and remembering what it means actually increases the strength of the links between the nodes. It increases the activation within the network. And as those things become strengthened, the meanings become, not more aware, the meanings become more instantiated within our cognitive networks, meaning that we learn things more. Things more readily come to our mind, or are more deeply ingrained in our memory, and thus more easily recalled. And when you look at fMRI research, this examines how changes in learning are often reflected in selected regions of the cortex and subcortex, meaning that as we learn something, it seems to be the case that there are certain changes that happen within the brain that actually reflect that. And what those changes are those changes are really indicating the formation of these kinds of networks and the formation of these kinds of meanings. So here's one model of one of these network connections. You can see that there's a lot going on to understand what a certain concept is. So we have an agent, Susan, who's actually giving to Maria a particular cat, and that cat happens to be white, and that Maria is also a president of a particular club. And so according to the ACT model, our understanding of these different things, of what a sentence means, such as Susan gave a white cat to Maria, who is president of the club. And the idea is that it's the network of connections for each of these words used in the phrase that allows us to find the meaning. Okay, I'm going to skip this one. And we've talked already about the parallel distributed processing approach. And why the PDP approach is so important for what it is that we're looking here is the models, so the network models that we're talking about are somewhat more theoretical and abstract. But when you start to place them into a parallel distributed processing network, you can see that these models actually could be related to how the brain works and how the brain actually substantiates meaning within different neural networks. So, certain cognitive processes can be represented by a model in which activation flows through the networks that link together a large number of simple neuron-like units. So then it's the case that networks, rather than specific locations in the brain, are where we hold different kinds of information. Okay, so there's four general characteristics of parallel distributed processing models. First off is that cognitive processes are based on parallel operations rather than serial operations. And we've talked a little bit about this before. Serial operations is the idea that you move from one process to another, or kind of in terms of what we're talking about here, that information would move from one part of the brain to the other. What a PDP model suggests is that there's actually multiple channels that are containing the information. So there's multiple areas of the brain that are activated when you're talking about a certain concept. And it's the parallel. It's several channels of, it's several different, it's a large neuronal activation, a spreading activation of different neural networks across several areas of the brain that embody the information that we have within our minds. So a concept contains activation in a lot of different areas of the brain, and that activation occurs in parallel, meaning that several different areas of the brain are contributing to the meaning of what something is. So, for example, if you're focused on more of the visual part of a concept, it's going to activate something more areas closer to the occipital lobe. Whereas if you're thinking about a less visual representation of a concept, it's going to activate more areas of the cortex, like related to the prefrontal cortex. So depending on how you're using or thinking about the meaning of the concept, there'll be different kinds of activations within the brain. But those activations are occurring in parallel, meaning they're happening simultaneously in different areas of the brain at the same time. So, secondly, the network contains basic neuron-like units, or nodes, which are connected together so that a specific node has many links to other nodes. PDP theorists argue that most cognitive processes can be explained by the activations of these networks. So the idea is, kind of even going back to this example we were looking at before, it's that this kind of setup is distributed among a network of different neural connections. And it's those neural connections working in parallel or at the same time that embody or allow us to see, that allow us to see the different kinds of information that we have. And so each node, if we think of kind of within the meaning of this sentence, for example, each of these nodes are going to be connected to other nodes that allow for the meaning of the sentence to actually come to our mind and for us to actually understand what's being said here. Okay, thirdly, the process of spreading information from one node to another node is called spreading activation. So that's the idea of meaning is spread out over the activation of several neural circuits working in parallel with each other, meaning working at the same time. So a concept is represented by the pattern of activity distributed throughout a set of nodes. So whenever a concept is coming to mind, the concept is coordinated with a specific activation of several groups of neurons or a network of neurons, and that concept comes to mind because that pattern becomes activated and stays the same over time. So concepts are contained in the pattern activation of neural networks within the brain. And that activation spreads, meaning it spreads to either different nodes in the network or different neural connections over time. Finally, fourth, this is consistent with the concept of situated cognition, such that the current context often activates only certain components of a concept's meaning. What this is trying to tell us is that depending on the depending on the situation or the environment that you're in, the environment will, in a sense, be a precursor or almost act as a primer for the types of things that will come to mind. It's kind of, we talked about this a little bit with memory. It's kind of like if you visit like your old high school and you haven't been there for a while, simply being in that space will bring to mind certain memories associated with when you were at high school. And it's the same kind of thing for our general knowledge, meaning that our ability to process certain concepts will be dependent on what kind of environment we're in, and the environment will have an effect on what kinds of meanings become activated with those things. Now, what's really interesting about the parallel distributed processing approach is that the memory can cope with partial and or partly incorrect information. And the idea is it's kind of like there can be certain holes in your memory about a concept, but that doesn't mean that you've forgotten everything about the concept. So, well, and this kind of often happens like when you're taking a test or something like that. When you're taking a test, you'll remember pieces of what it is that you're trying to remember, but maybe there's a small part that's missing. But even if that small part is missing, you're still remembering several other facts that'll be connected to that particular concept. And so the idea is that PDP processing can actually account for this. And how it accounts for that is by saying that when you have a missing piece of information, the reason that piece is missing is because the network is not fully activated, meaning that the network has not kind of, in a sense, grabbed onto that piece or activated that piece of the neural network that's connected to that thing that you're trying to remember. However, it's still the case that at least several parts or facts or parts of that concept would still remain. So you can still remember a lot about certain concepts, where they came from, who started them, what year they started, so on and so forth. But maybe you're missing one little bit of information about that. And the idea would be that because things are working in parallel, there's room for a certain amount of mistakes, or there's a room for certain kinds of missing information um, without losing the whole thing. Just kind of a few features to discuss regarding the PDP model to kind of finish up here. Um, so first on, the connections between the neuron-like units are weighted, and the connection weights determine how much activation one unit can pass on to another unit. And so by weighted, we mean that activation, well, one way to kind of think about activation is a unit can be activated at a level of, say, 1 to 10. And based on the connection weights, you can change that level of weight to either be like plus 10, plus 7, plus 5 or 4, so on and so forth. And it's the strength or the weight of those connections that plays an additional role in how the network itself becomes activated and the pattern that's formed within the neurons. Kind of another way to think about this is when a unit reaches a critical level of activation, it may affect another unit either by exciting it, if the connection weight is positive, or by inhibiting it, if the connection weight is negative. So you can have various levels of weight or levels of activation, and then additionally, you can have those weights can either be excitatory, meaning they're trying to promote the activation of other units close to it being activated, or it can inhibit the activation, meaning it's trying to decrease the likelihood of those weights near it to actually be activated. So thus, every new piece of information you learn will change the strength of the connections among the relevant weights by adjusting the connection weights. And what this is basically telling us is some of the more important nuances of how the pattern emerges, how this pattern of neural activation can be modified over time and can be strengthened based on the existence of weights. And that that strengthening can either occur in a positive way through an increased or an excitatory factor of neurons, or it can be inhibitory, or it can be reduction in terms of lowering the weight of certain connections. So sometimes we only have partial memory for some information rather than a complete and a perfect memory. We've talked about this a lot kind of throughout the class, is that memory is not perfect. Memory is not fully objective. Memory fades for a variety of reasons. And what the parallel distributed processing model gives us is it gives us reasons for why memory can sometimes be partial, or why memories can sometimes fade. And it's not that everything is gone. I mean, though obviously it's sometimes gone, but a lot of times we can have pieces of a memory or parts of a memory. We can recall certain things about a memory and not others. And what this may be reflective of is this difference in terms of the activation that's occurring and the loss of parts of a pattern, and the strength of, or the excitation of, other parts of the pattern. So it's the brain's ability to provide partial memory is called graceful degradation. And this is something like the tip of the tongue phenomena. The way that you can remember, it's like when you see someone and it's like you know that you know them, you're recognizing them, but you can't exactly remember their name. Or you can remember their name, but you don't remember where you met them. It's those kinds of things, and that's the graceful degradation that occurs. It's the way in which memory fades, and the idea behind how memory fades is that the networks that are instantiating the representations or the memories that we have, those things fade. When things are not used over time, it begins to degrade, and we see those same sorts of things within PDP networks. So the current status of this theory, it's generally consistent with the neurological design of neurons in the brain, which really gives it a strength to a certain extent. Tends to work better for tasks in which several processes typically operate simultaneously. That goes to that working in parallel notion, and in which networks must learn about pattern input that is highly structured. So for pattern recognition, something I may have talked about before, facial recognition does really well in these kinds of networks as well. All right, so that's it for this part of Chapter 8, and I'll talk to you later.